Started.
All right, good evening, everyone. Welcome to CAPA Leadership Peer Support Program Special Lecture Series tonight. My name is Helen Zhang. I'm the chair of the CAPA Leadership, Professionalism, Awareness, and Friendship Development Program, and will be serving as your moderator tonight. It is our great honor to introduce our guest speaker today, Dr. Richard Coate. He's from Washington University in St. Louis School of Medicine. And let's surely introduce Dr. Coate.
All right, thank you, Helen. Hey, everyone. So it's my great pleasure to introduce Dr. Richard Coate, who is the Edward Mallinckrodt Professor, Chair, and Professor of the Department of Pathology and Immunology at Washington University in St. Louis School of Medicine, and the Chief Pathology in Chief at Barnes-Jewish Hospital. Dr. Coate earned degrees in chemistry and biology at the University of California at Irvine, and he obtained his medical degrees from University of Chicago, and then he did his residency training, pathology residency training at New York Hospital Cornell University Medical College. He then finished his fellowship training in pathology at Memorial Sloan Kettering, and then did did tumor immunology at Memorial Sloan Kettering, followed by a molecular pathology at New York University School of Medicine, and he started his career at the University of South California School of Medicine and rising to professor in the Department of Pathology and Urology and the director of the GU Cancer Program, and later was promoted to the chair, Joseph Kuttner Junior Chair of Department of Pathology and Professor of Biochemistry and Molecular Biology. He's the founding director of the Dr. John McDonough Foundation Biomedical Nanotechnology Institute at the University of Miami. And Dr. Coate joined Washington University in St. Louis 3 years ago, and at Washington U, he did a fantastic job in many aspects of pathology and in scientific discovery, clinical innovation, and also education of our next generation of physicians and scientists. So, he particularly I want to mention relevant to our talk. He has led the transition to subspecialty care at Washington U and recruiting some of the most outstanding pathologists in the country, and also he bring up the subspecialty pathology care to the partner hospitals of Barnes and Jewish hospitals, and we just finished converting the Jewish Barnes Western County Hospital, so to allow that hospital to have subspecialty pathology care. And this is truly, is a transition from the traditional pathology service to a unprecedented subspecialty pathology to those small hospitals. So this is something I truly want to mention. And also Dr. Richard is truly a research, academic pathologist, and he has done many researches, and his major interest is in tumor biology from the early metastases and the tumor biology, and he's very interested in the circulating tumor cells, its detection, its biology, and he has published over 300 publications and with many pathology textbooks in his expertise in his field. And he is the recipient of big numbers, $190 million of fundings, and including almost 50 million as a principal investigators. Okay, so that part I truly want to, impressed me. And not only that, Dr. Coate has, great leadership. He's a member and advisor to many national, international societies, organizations, including the NCI. And he was awarded the 2013 Distinguished Alumni of the Year by the School of Physical Science at the University of California, Irvine. And, to make the story short, he was in 2021, Dr. Coate was elected to the National Academy of Inventors. Dr. Coate is also, very active in the entrepreneurship. He is the founder of several technology-based companies, include Impass Inc., which is the first company to bring exoteric testing for cancer analysis to the market, and which under an IPO in 1996. And also one of the company, probably many of us are very familiar, is Clariant, and which is acquired by GE in 2009. So Dr. Coate has, advised to many industrial companies, and so it's to me, Dr. Richard Coate is embodied all aspects of a great academic pathologist. So today I'm very fortunate to invite, Dr. Richard Coate to speak to us. And Richard, without further ado, please take the podium.
Thank you very much, Shuli and Helen, and all of the members of the leadership of the Chinese American Pathology Association, and all of you who are participating. I see that there's 150 of you out there on a Sunday evening. I'm very impressed with that. It shows a great deal of both intellectual and physical energy on your part, and I appreciate it. I also want to just mention that we recruited Dr. Shuli Liu, Shuli, about a year ago or so, and I am so pleased that we were able to recruit her. She's been an outstanding leader for our GI program, and as you all know, she's one of the world's foremost GI and liver pathologists. She's really elevated what was already a very good program. And I'm so happy that you all have recognized her leadership and her excellence by having her as your incoming president of the Chinese and American Pathology Association. So Shuli, Helen, leadership, and all of you, thank you very much for inviting me to do this. Today, let me go ahead and share my screen here. Today, I'm going to be discussing with you, let me just go ahead and minimize, you probably can't even see that, so perfect. Speak to you about the digital future of pathology. This is an area that I have been interested in for several decades. The company that you all may know as Clariant was first started as a digital imaging company called Chromovision. And I got involved with that company in the early 90s as one of using that technology in one of my primary applications, which was the automated detection of circulating tumor cells. And later came back to the company to execute the transformation of it from Chromovision into Clariant. In addition to that, I've been very much interested in using digital pathology to enhance and democratize our pathology expertise. And I'm going to be speaking a little bit about that, and also a little bit more broadly about just how this new age of digitalization is really transforming the world of pathology, using a couple of specific examples for that. So, as we think about the future of pathology, some of the work and the visions that my colleagues and I have had is really transforming how we use the microscope itself, our oldest tool, by applying deep learning, artificial intelligence, and highly multiplex molecular spatial profiling to histologic images, allowing us to see much more deeply into a histologic image, and indeed to go beyond what it is that we can actually see in a histologic image. I'm going to talk to you about some really interesting work that I'm doing with my longtime collaborator at Caltech, Cheng-Wei Yang, in the development of a new form of microscopy, which allows for all-in-focus imaging. As I just mentioned, the use of pathology to democratize expertise, I think, is something that is already happening, and we have a very fine example of that here at Washington University, and I believe that we will that this will expand as time goes on. There's no question about that. And then finally, I'm going to talk a little bit about sort of the next frontier in our electronic medical records. As we all go to digitizing our EMR, how can we take advantage of that by using artificial intelligence to enhance our ability to mine the EMR and really to enhance prediction, prognosis, management, and enhancing individualized patient management. All right, so let's just go ahead and jump into this. What I will start with here, just move this around a little bit. If I just for myself, you guys probably can't even see that. Our understanding of using histopathology in pathology, of using histologic images in pathology, really took fruition in the mid-1800s through the work of Rudolf Virchow, who you all know, particularly in his seminal work, Cellular Pathology, in which he actually describes for the first time the histopathology and the origin of tumors. Now, he didn't get everything right in that, but it was certainly a transformative event. And here is an example of his own drawing of breast cancer. And all of you on this call can probably recognize this as a ductal carcinoma in situ, then with chemotonecrosis and with infiltration of single tumor cells in the area, looking very much like what we would see here in a modern histologic image. And so really the ability to look down a microscope at a thin section of tissue that's been stained with vital stains, and to start to recognize that into different normal and pathologic entities has really been around for nearly 200 years, and in many ways is unchanged from that initial breakthrough. Obviously, we've added a new technique in electron microscopy, and then we've added the ability to look more deeply in these tissues through molecular analysis, and also through immunohistochemistry and other in situ applications. But what can we do to actually go beyond this histologic image? How can we use our modern computational technologies to help us to make better diagnoses and maybe even go beyond what it is that we can see? Let's see, I don't know. Oh, here we go. So first of all, let's talk about what artificial intelligence and deep learning are, and some of the differences between that and machine learning, because many of you will know about machine learning, but doing deep learning and artificial intelligence is really fundamentally different. So in traditional machine learning, which is also a computational exercise, you have an input that there is something, an object. It could be a car, it could be a cancer, it could be a specific type of cancer, in which we, and in our case, the pathologist, extracts features that we know about within that object. If the object is, for example, breast cancer, we could be considering things like nuclear to cytoplasmic ratio. We could be considering things like invasion through a basement membrane, infiltration, stromal responses, that sort of thing. And we add those features to a classification, and then test that by asking, is the algorithm able to identify a car versus not a car, or a cancer versus not a cancer? So that's kind of traditional machine learning, using those manually defined features. But what we want to do in deep learning is to go very much beyond that, and to extend beyond the limitations that we as humans have in extracting features from a car or from a histologic image. And so really what deep learning does is it takes that input and it does its own feature extraction and classification that may be very opaque to us as we go through this. And I'm going to show you some really interesting examples of this, and then gives us an output that is either, in this example, car or not car, but did it in ways that may have little or nothing to do with the parameters that we would use, or certainly would use parameters that go beyond what it is that we can see and recognize. So, so in this process, I will give you an example from my own work on circulating tumor cells. So we have, in some of our current work actually, are looking at automating circulating tumor cell analysis, but also not just circulating tumor cells, but also circulating cells of the tumor microenvironment, which we have shown in our research to be really important in establishing a prognostic classification for patients with cancer. Now, that seems kind of simple. So what we have to do is just recognize the tumor cell and maybe a couple of other cells, and that seems like maybe a simple problem, but it's actually quite complex, because we have to have the algorithm recognize CTCs, circulating tumor cells, recognize circulating cells of the tumor microenvironment, in this case, cancer-associated fibroblasts, and also other cells that will be seen in a blood sample of a patient with cancer, which would include, of course, white blood cells. So we need to see all of these, and we need to see them combined. But even within the CTCs themselves, the deep learning algorithm must learn to recognize and distinguish between multiple CTC morphologies. And these morphologies may in and of themselves have great prognostic significance. So for example, we have shown that CTCs can manifest themselves as in what we call a spheroid way, that they can manifest themselves as spindle cells, and that they can be clustered, as you can see here, multiple CTCs within a cluster, and here another example within this clinical sample. And we've shown that these different morphologies and clustering of circulating tumor cells, and also clustering with circulating cells of the tumor microenvironment, such as the cancer-associated fibroblasts, is really important. So you see that what would first seem to be a relatively straightforward problem becomes a very complicated problem for the deep learning algorithm to recognize, even in this relatively non-complex example. And so this is the challenge that we were faced with, and we've now done a fair amount of work. And I just want to show you the results of some of our initial analyses in our work with our colleagues at Caltech. So the way that this is done, by the way, is that you first provide the algorithm with training images in which the pathologist has marked the subjects that it wants the algorithm to concentrate on. So it says, okay, that's a CTC, this is a CTC, this is a CTC, and trains the algorithm, and then it goes and tests the algorithm. So we did that. We did training of this algorithm, and then we went to testing. And what we did in the testing was that our laboratory technicians and pathologists actually marked the CTCs in the testing images, and then asked the algorithm to go ahead and enumerate, identify and enumerate the circulating tumor cells. So here was a test image, and our pathologist said, well, here's the CTC. Here's another test image, and the pathologist said, well, here's the CTC. But the computerized neural network, this AI algorithm, actually identified, here's the one that the pathologist had identified, but the computerized neural network identified all of these spaces. And my colleagues at Caltech in our regular lab meetings said, you know, this failed. We didn't get it right. We're not finding what you found. We're finding so much more. And when we looked at this, what we recognized was that the pathologist circled this one and identified this particular CTC because it was in focus. But these were out of focus. But as it turns out, all of these that the machine recognized are CTCs. So this was actually a great example of the power of this particular technology. Not only was it able to recognize the good example in this digital image, but it was actually able to recognize the poor examples in this digital imaging. And our current analysis indicates that using the artificial intelligence algorithm, what we call here the computerized neural network, we can achieve an accuracy of nearly 90% in detecting CTCs and distinguishing them from other cell types. We are now moving on to clinical samples. These are model samples. We are adding we are asking the algorithms to look at the different morphologies of CTCs and the circulating cells of the tumor microenvironment. And as you can imagine, this will hugely simplify the analysis of these rather complex preparations of circulating tumor cells. And the next step, of course, will be to use the artificial intelligence to not only identify these CTCs and other associated cells, but also to predict, to identify prognostically significant features within these preparations. So, for example, not only identifying clusters and clusters with circulating cells of the microenvironment, but asking what are the features that are correlated with the ultimate outcome in these patients. And so that's all part of ongoing work that we're using. Here's another example that was developed by two of our faculty members, Joe Gott and Josh Slamidas. This is automated glomerular analysis using AI. Some of you may be involved, for example, in the evaluation of donor kidneys, particularly from cadaver donor kidneys. And what needs to be done there is that a piece of kidney is taken and then it's stained, and then a pathologist needs to analyze these preparations in order to identify the globally sclerosed from the non-globally sclerosed glomeruli. And of course, if there is too much sclerosis, those kidneys are rejected and they aren't used. What Joe and Josh did was to develop an AI algorithm that was able to distinguish between two very similar physical features, and that is a sclerotic glomerulus versus a non-sclerotic glomerulus. And they found that the annotated specimen from the AI algorithm was very, very similar to the predicted specimen. Now, what this allows for is a very reproducible way of quantifying functioning from non-functioning glomeruli in a way that is probably more reproducible than human observation, and certainly more quantitative than human observation, and that Joe has shown has the ability to significantly decrease the donor kidney discard rate because it comes up with a much better quantification for these kidneys. And so this is actually already available. It's known as Trusted Kidney, and it's being used in trials currently to evaluate donor kidneys. And so that's yet another application. Now, the two examples that I just gave you, identifying CTCs and their accompanying cells, and then identifying and distinguishing sclerotic from non-sclerotic glomeruli, are applications of artificial intelligence, of AI, that assist us with things that we can already see and recognize. Right? So in other words, I can recognize a CTC, I can recognize a cluster of CTCs, I can recognize a cell from the tumor microenvironment, a circulating tumor microenvironment. But what the AI did in those last two examples was to help us to do it better, faster, easier and more quantitatively than we as humans can do it. So it's just an extension of our eyes. But what about doing things that we can't see? What about using AI to go beyond our ability to see what's on the slides, or at least to interpret what we see on the slides? Can AI actually interrogate histologic images and do things that we as pathologists have very difficult time doing? And of course, in the case of cancer, that would be, for example, to predict whether or not a primary cancer is going to go on to develop metastases. We have a very good model for this at Washington University. Ramaswamy Govindan, who's the head of our solid tumor service, has collected along with Mark Watson, again, one of our faculty members in pathology, has collected a series of early stage non-small cell lung cancer primary resection specimens, and has followed them for a period of time and has developed a cohort that developed metastases, in this case, specifically brain metastases, versus those early stage non-small cell lung cancer specimens that did not go on to develop metastatic disease. So, a very, very important distinction, identifying cancers that are going to spread versus identifying cancers that are not going to spread and metastasize. Now, in the case of non-small cell lung carcinoma, of course, our histologic analysis, our ways of doing that, really are quite inadequate. And here, for example, is tumors from a patient whose cancer metastasized, eventually metastasized, versus tumor cells from a patient that did not eventually metastasize. And remember, these are all stage 1 and stage 2 patients. And you can see that you just can't tell the difference. One cannot make that distinction simply looking at the histologic image. So we asked, could these computerized neural networks, this AI deep learning, applied to these biopsy samples, actually help us to predict which ones were going to metastasize and which ones were not going to metastasize? We went through the same process. So here's an example of a resection specimen from a patient with early stage non-small cell lung carcinoma. We took these images and we subjected them to the AI algorithms. We first did the training set, where we said, okay, these samples are samples from patients that develop metastases, and these samples are samples from patients that did not develop the metastases. And we simply allowed the algorithm to try to make out anything that it could to distinguish these. Our first analyses were really interesting. It looked like this was going to, that the algorithm could in fact do this. We then went back and asked, well, are we overreading these? And we did another sort of sanity check on this, where we separated out the tumor biopsies based on the first letter of the patient's last name. Now that the computer should not be able to distinguish between the first letter of the patient's last name. And in fact, the algorithm was not able to distinguish cancers that were separated on that basis. And we've done a number of other things to really address whether or not what we're seeing is a real phenomenon or whether it's just an artifact of this process. And so far, we have come up with nothing. And what I want to point to here is that the ability of the algorithm to do this actually really stunned us. And what we have seen, and it's getting better and better as we do more and more testing, is that the prediction accuracy seems to be greater than 95%, which really would give us great data as to the tumors that are likely to metastasize versus those that will not metastasize. Now, the other thing that's interesting and that I want to focus on next is that we also have the ability to ask the question, well, what is the computer looking at? What is this AI algorithm looking at within these samples? And this is a heat map of the algorithm's analysis of this biopsy specimen. And what you can, and the more orange the color, the more the algorithm is concentrating on those areas. And of course, what you recognize is that the algorithm does appear to be mostly concentrating on the area where you can see the tumor cells. We also see some concentration out here where there may actually be some tumor cells or some kind of stromal reaction out there. These are not normal areas, as you can recognize. But in the areas of the more normal appearing lung, we don't see this does not appear to be areas that the computer was able to use to make the distinction between those cases that would metastasize and not. We actually can go down deeper at more high power and ask the question, well, again, what is the computer looking at? And one of the things that we have noticed is that it doesn't necessarily appear to be looking oftentimes at the cells themselves, but rather at the stroma between the cells, which begins to make a lot of sense as we understand that stromal interaction, particularly involving lymphocytes, may have a very important impact on progression of these tumors. And what our plan is to really validate this finding now in a large multi-institutional cohort of patients with early stage non-small cell lung carcinoma. And then to do a molecular exploration that focuses on the areas that the algorithm is focusing on, to ask the question, what is the molecular basis of what this algorithm is looking at that allows us to make this kind of prediction? So we're really excited about this work and where it seems to be taking us going into the future. And it's just an example of how we may be able to use artificial intelligence and deep learning to really go beyond what it is that we have the capacity to recognize. In other words, going beyond seeing, and then use that data to come up with a better biological and molecular understanding of what the basis for that is. The next thing that I want to turn to is molecular profiling of tissue, which all of you are familiar with, and we use it every day in our practices, and which is very, very powerful. We depend on it, and yet it has a limited capacity. So here's an example from some early work that I did that actually established the prognostic importance of micrometastases in the lymph nodes of patients with breast cancer. So here's a lymph node that was initially called negative in a patient with early stage breast cancer. This was a node negative patient. And using simple immunohistochemistry, what we were able to see is collections of tumor cells. This is a very simple example that all of you will use. We can go a little bit deeper than that, again, using some of our data from our CTCs, where we have very few cells that we can study, and we want to try to get as much information out of those cells. We can do multiplexed immunofluorescence. On that, we can do RNA in situ hybridization and DNA fish on these samples. But our ability to do highly multiplexed analyses in these kinds of situations, including on histologic samples, is really limited. We can take these tissues and extract proteins and DNA from them and get a lot of information that way. But that then loses that spatial information, which we all know will be very, very important to us. So how can we address that problem? And there have been new technologies that have been developed specifically for molecular spatial profiling. And this is an example from Bob Schreiber's lab. Bob Schreiber, as some of you may know, he's again on the faculty of pathology and immunology at WashU, is really the father of tumor immunology. And what he is using is a highly multiplexed imaging platform to be able to look at many different immunohistochemical markers simultaneously while preserving their spatial profiling, and has shown that spatial profiling gives very important information with regard to tumor biology and response to tumors. And this is an example of where he has looked at the response of tumors to immune checkpoint inhibitor therapy. And you can see these very complex profiles that he is able to produce in examples. This is for the control antibody, where we see very little tumor response. Here we see a lot of tumor response, and we can see the various areas of tumor response as defined by these phenotypic and biologically important markers for this. And so this really has these kinds of technologies also available for gene expression, for RNA analysis, really will allow us to hugely expand our ability to understand molecular relationships as they relate to actual morphology of what it is that we're looking at, in this case, tumors. I think that some of you will have the same experience as me, the older ones of you, where, you know, in my training, and this is now going back to the late 80s and early 90s, I was told, well, you know, you really shouldn't go into pathology because it's not going to exist in another, 5 to 10 years. We will be able to do everything that you do as a pathologist just through molecular biology. And as you can see by your practices, that hasn't turned out to be the case. And one of the reasons that it hasn't is that it isn't just what's there in a soup of extracted from a tissue, but it's exactly what we're seeing here, this kind of histologic, this morphology associated with these very fine molecular details that are providing us with the kind of information that we need. Okay, let's move on and talk about the microscope. We all use the microscope. The microscope's been around for a long time, developed in the 1600s, and actually Van Leeuwenhoek would recognize today's microscope easily. He would recognize that it has all of the things that his microscopes had: a light source, a lens, and a way to look at that at the specimen. These are microscopes that I have, old microscopes that I have, and again, same thing. We have a light source, we have lenses, and we have lenses here, and then we have the ability to look down, focus, and look specifically at those areas. So it's really kind of remained unchanged for centuries. Well, again, that's been obviously a wonderful technology, but it in some ways doesn't address the challenges of the new pathology, particularly of digital pathology. And I want to show you an example of that. So, again, as I've said here, since Virchow's time, we've used thin pieces of tissue placed on glass slides with a single light source illuminating the tissue, and then sending this image to the lens, right? To the eyepiece, to the lens, and then up to the eyepiece. And we can manipulate this pretty well. But one of the things that, if you just think back to looking at the microscope, is that there is no piece of tissue that you have ever seen that's all in focus. As you go through and you look at the tissue, you are always constantly making fine adjustments in focus with your adjusting mechanisms, and that's fine. We do that very well, and we do it even without thinking. But when you collect a digital image of that section, of that histologic section, those aberrations in focus become critically important. And what you have are some areas that are in focus and some areas in the same plane of focus that are out of focus. And what this actually results in are images that actually become very suboptimal for artificial intelligence, which really requires an all-in-focus image to make any sense of it at all. And in fact, Phil Nelson, the head of Google Imaging, and one of our collaborators, has said that about 90% of digital images have defocus issues. And for artificial intelligence, what that means is garbage in and garbage out. And we believe that it's one of the reasons that artificial intelligence has had a difficult time being established and being useful in the area of histopathology. Now, there are ways, rather complex and very computer-consuming ways, of dealing with this by taking multiple planes of images of multiple planes and then analyzing those many planes. But again, that requires enormous computing power, and really for routine analysis is impractical. Well, again, in collaboration with my colleagues, Cheng-Wei Yang and his group at Caltech, we have been looking at what I think is a radical innovation in microscopy that Cheng-Wei invented now just a number of years ago. And that is Fourier tychographic microscopy, what we call FPM, that produces in one scan an all-in-focus image. Now, how does it do that? Well, it does it through a radical innovation in the microscope, and that is instead of using a single light source, what FPM does is to use multiple, even hundreds of light sources in a specific way. Okay, and so this is the example of it. This is, for example, an LED from a single point all of these points that you see here are different light sources. And these different light sources approach the sample here at different angles. Now that's really important because when they approach it at different angles, what they are doing is they are then coming up to the lens at different focal planes than as opposed to just a light source that comes straight up through that image. So it's taking, basically it's acquiring in one swoop images at different focal planes within the tissue that's being assessed. And what the the Fourier tychographic transformation allows for is a reconstruction of all of those images into a single all-in-focus image. It's really a paradigm shift in the way that we deal with aberrations. And I'm going to show you here a really quick example of the power of this technology in something that we have just recently published. Actually, it's not in review, which just a couple of weeks ago was published in the Journal of Pathology Informatics. In using this FPM microscopy in fine needle aspirate preparations. Now, you all know that a fine needle aspirate preparation, if a histologic section, a thin section, has aberrations, well, these are very thick specimens and they have all kinds of aberrations. And that can be challenging even for a cytologist to go through, because one has to focus up and down through that image. So here is a cluster from a thyroid FNA in a single plane of focus. And you can see that large areas of this are out of focus, as you can see here. And I'm going to come back to these two areas in just a moment, okay? But let's focus on this. And this is the image that was produced through the FPM microscopy and then the Fourier transformation. And what you see here is that this cluster is now all in focus. In a single image is all in focus, allowing us to see great histologic detail in these areas as well as these areas that were already in focus, even making out stacks of cells or cells that are on top of one another. Now let's take a look at these two boxes right here, because it kind of looks like even here and here that those were in focus. But when we take a closer look at those boxes, we can see that, well, not really all in focus. We can see these areas out of focus. And on the FPM, we can see that they become in focus. In this one, we see two cells, but actually the FPM shows us it isn't actually two cells, it's three cells here when we can see it all in focus. So again, we think that this not only could be a really great innovation for routine cytologic analysis, but also that these all in focus images will be well suited for deep learning processing as well. I'd like to then move on, and Shuli, I noticed that we're coming, and Helen, I noticed that we're coming to the end of the time. How much longer would you like me to go? Because I can end here or I can just keep going. Tell me what you'd like me to do.
You can go ahead.
Yeah,
Okay.
you can go as long as you want.
Yeah.
Okay, I just wanted to make sure that that was going to be okay. All right, so next I want to talk about using digital pathology in democratizing expertise. Democratizing expertise is just a fancy way of saying allowing our expertise as subspecialty pathologists to be useful throughout the community and in areas where that expertise may be difficult to access. So here's an example. The example is What happens when a community pathologist in a group of, say, 3 or 6 pathologists that does general pathology has a difficult case and wants to access a subspecialty pathology review? Well, the typical thing is to send the glass slides by mail, wait days and weeks, have the chance of the glass slides lost, get an answer some other time further from that. Well, but you can get an answer. But what happens when they need an answer right away? For example, in an intraoperative consultation, there's no ability to access deeper expertise in that kind of situation. So how can we address this? And obviously we can do that through digital pathology. So we have been doing this now at our institutions. I actually started this when I was at the University of Miami, and we've incorporated this in our practice at Washington University, where we use now very well established scanning technology to produce high quality digital images. And then we're able to transmit those images anywhere in the world that can revolutionize access and provide advanced pathology access to, for example, underserved populations. Now, I want to give you an example of what it looks like to go to assess a digital image, because in my view, it actually is digital images may actually be easier and better to look at than a microscopic slide. So here's some liver biopsies that have been taken. This is the initial image that was taken, and this was accessed at relatively high power. And this is how you can go through this slide by easily going through, adjusting, just using the mouse, the magnification of this, easily going through these sections, locating areas of interest, actually being able to mark these areas of interest, and doing so basically anywhere that you have access to a high quality computer monitor or an iPad, a phone or an iPad, which has, you know, as high quality screens as we have. So very, very facile technology. And so again, using this to create access to subspecialty pathologists, for example, those at WashU, digitizing glass slides, enabling help with primary diagnosis and even intraoperative consultations, and certainly for the kind of difficult case review. We have implemented this now at 2 locations, remote locations in the Barnes-Jewish system, where pathology, and in particular frozen sections, are being reviewed remotely at locations which, in the case of Barnes-Jewish West County Hospital, have no pathologists on site, and in the case of Memorial Hospital Belleville, will soon have no pathologists on site. And we are able to provide not just the same pathology services as before, but actually highly enhanced pathology services, subspecialty reading of frozen sections and of primary diagnosis of cases. And some of you will have gotten a good dose of this, because we know that telepathology and digital images really were essential to our practices during the pandemic, where, for example, we weren't allowed to sit across from our residents. Well, how did we manage that? We managed it through, again, digital and telepathology, in the training of our residents. So again, really revolutionizing the way in which we practice pathology. I'm going to go through the rest of this pretty quickly, although I think that there is really a lot of promise in this next area of mining the electronic medical record. For example, I'm going to give you examples of enhancing patient safety, anticipating problems, and advancing personalized medicine, and even addressing healthcare disparities. So I want to first talk about, some simple examples of adding value, improving the experience of care for patients using the electronic medical record. And this was something that I started at the University of Miami, at the University of Miami, and that we are now extending in our work at Washington University, where what we have focused on is mining the laboratory data within the EMR. And we really like that focus because, as some of you may already know, laboratory data represents over 60% of the information in the electronic medical record. So it is a rich source of data, and which is largely already digitized, that we can access in order to perform additional functions. Now, in this particular case, I'm giving you some pretty simple examples of where we have used data from the laboratory information system to, for example, flag critical results. And we've used the EMR to do this. And this is not just the urgent results, but the critical results, such as a first diagnosis of cancer or an unexpected result. Flagging the EMR in order to alert the clinician that you have a first-time diagnosis of cancer, you have an unexpected result, you have a discrepancy between your frozen section and your final diagnosis. And we need you to be aware of this and to take action. And so we create these flags. And what this does is it ensures that the primary physicians take action. They have to, when they have to close these open encounters, they have to document the patient follow-up. And so that's one aspect of it. The next aspect of it that many of you will be familiar with is that we're using the EMR to provide direct patient notification of laboratory results, even including histology reports for this. And this actually provides us a portal through which patients can know that they have a result and can themselves contact their physicians. And this really represents a risk mitigation strategy. When I got to the University of Miami, and then again at Washington University as chair, I was presented with the history of medical malpractice. And not all of them, but nearly all of them had to do with diagnoses that were made correctly, but were not adequately communicated to the physicians, to the clinicians. They were unexpected results where the physicians, the primary physicians, were not notified. And so this really helps to mitigate that risk. And then, of course, ensuring clinical follow-up through enterprise scheduling. So that's a pretty simple example of how we can use the EMR to add value, mitigate risk, and make for a better patient experience. Now, we also have other goals in terms of mining the EMR, and that would include helping us to, for example, use the data to understand drug response prediction, to do better clinical decision support, and to do much more personalized, patient-specific precision medicine, in addition to some of these other things, including anomaly detection. And I'm going to give you some specific examples of this that show the power of being able to mine the CMR. Well, one great example is in one of the chronic diseases that really represents a major source of healthcare expenditure, and that is the management of patients with diabetes. And so we can use the EMR and lab data to help us to identify outliers, manage to optimal values, and identify treatment gaps. So here's an example of this. We have a known diabetic who comes up with a hemoglobin A1C of 14.2, obviously way higher than we want to have. We can do risk assessment of these patients using standard risk assessment procedures. We can help through this to manage these patients down to more acceptable control of their diabetes, but also we can use the EMR to document whether or not these patients have been followed for things that could be related to their diabetes but haven't been followed. For example, an annual eye examination. And so again, and these are examples that are now being used. Identify at-risk individuals and institute interventions before catastrophic complications occur. And I consider this to be, on a patient-by-patient basis, a true precision medicine approach. Now, what about going beyond that and actually using the EMR to anticipate problems that before they actually occur and give us a chance to intervene? This is actually an example that was recently published on acute kidney injury. As you will know, acute kidney injury is a very common problem in hospitalized patients, particularly in those in the ICU. And when acute kidney injury occurs in its manifest form, those patients become then high risk for developing chronic kidney insufficiency. And so how can we approach this? Well, in this example, these investigators looked at the EMR in a very large cohort of hospitalized adults. And what they were able to show is that they, through this model, were able to recognize incipient AKI before full-blown AKI actually occurred, and were able to do this as much as 48 hours before the actual clinical diagnosis was made. And so with that kind of advanced knowledge, the next steps here are, can we intervene in these particular cases in order to mitigate this and intervene at the earliest possible time? This is an example of work that's being done in our department by one of our residents, and Chris Farnsworth, that uses the EMR data to actually address healthcare disparities. And so what Vahid and Chris are doing is using EMR data and mapping, they're mapping lab data to census tracts and to areas of social vulnerability. And we know that in, for example, the St. Louis areas, that the vulnerable patients, St. Louisians, have poorer diabetic control. So how can we start to integrate that that demographic data with our interventions? And one way of doing this that they're doing in this is to do, for example, hemoglobin A1C testing in the Barnes Jewish Hospital emergency room when patients come in who have been identified as with a higher index of social vulnerability based on these kinds of data. So again, using the EMR and using these kinds of analytical capabilities to even address healthcare disparities. So we're entering the world of a new pathology. We're able to make our expertise much more accessible for better, faster, and safer patient care through our digital pathologies. We're changing our tools to adapt to new challenges. And I gave the example of a radical change in the microscope that is addressing the new challenges that we have with digital image acquisition and artificial intelligence. We're using new technologies that will allow us highly multiplexed molecular spatial profiling for a whole new paradigm in tissue analysis. And we're using AI to do things that we can't do, that we can't see, to allow us to use our histologic images to predict the biologic potential of these histologic images. And then, of course, mining the EMR to produce personalized medicine. So I have gone a little bit over time. I am very happy to go ahead and take any questions. I want to once again thank you all for allowing me to come and be with you today. And truly happy to take any questions.
All right, thank you, Richard, for giving us such a a great talk. Touch many aspects of the pathology future, I would say, from the digital pathology and to the AI, and also to a type of new scope, and also mining the EMR. It's truly we have a lot of space. We can explore a lot of tools. We can to play with. Let me say this way. So there are two questions. So we go to the question directly. Okay, so Hannah, would you mind, go to the question, the Q&A?
Sure, yeah, okay, so it's a great lecture. We have a lot of questions, I believe. So the first one is from Dr. Xiaofei Zhang. So he typed, okay, thank you so much for the excellent presentation. What's the depth of field for FPM? Do you need special lens to improve the FPM?
Yeah, that's a very good question. The depth of field is in the tens of microns, so it can actually assess relatively thick specimens like an FNA specimen. There are other mechanisms now that we can start to do this. For example, confocal microscopy, a little bit more challenging. But FPM is really a very fast way to acquire these images. You do not need special lenses. The FPM is used with just standard microscopic lenses, so that one does not need special lenses.
Yeah, that's actually the question I was thinking. So you just build in with your existing regular microscope, right? You don't need a brand new one.
Yes.
Okay. Yeah. And the next one is from Dr. Lee. So he typed, how soon do you think a scanner using FPM technology will be available for cytology practice?
So their FPM scanners are available. What we're doing now is refining this for these kinds of applications. It's a great question because I think that this could be very, very useful in cytology practice. So we're hoping to have this available, within the next couple of years at the latest.
All right, so the next one is from anonymous attendee. Thanks for the excellent talk. As a new graduate resident, there is minimal, if not zero training on AI in pathology during my training. Do you have any comment on education regarding AI in pathology for the future generation of pathologists?
Yeah, that's a really great question and comment. And indeed, I think that what we need to see going forward, and in fact, this is something that our own residents have really asked us for, is a lot more focused training in digital pathology and in techniques such as AI that can be applied in digital pathology. So we are planning at WashU to add this as part of our residency training curriculum. And I think that one is going to see this more and more happening as this resident will know that you know, all of the board exams now are taken remotely and using digital images. And if you haven't been looking at digital images, that can be challenging if you have, you know, when you're just confronted by that during your board exam. So, you know, there's some immediate aspects of this that we want to address as well.
Okay. Next is from David Zhang. What whole slide scanner used in your institution?
Yeah, that's a good question. We actually have been using several of them, including Microscan, Apereo, and there's some others, and we're about to evaluate more. I would say that that all of the systems that we have used so far are actually very good. What their differences are is somewhat in the speed of scanning, although now the scanners, recognizing that they have to be fast, are really pretty fast. And then the number of slides that it can handle. So the kind of scanner that you would use in a frozen section evaluation, a frozen section room, wouldn't necessarily be the kind of scanner that you would use if you wanted to digitize all of the histopathology slides that were coming out of a laboratory.
All right. So next question is from Dr. Yu. In CTC study, what's the ground truth of the cell types? Yeah,
that's a very good question. So the ground truth for us has been the pathologist's interpretation of morphology and then the molecular phenotype of the cells. So for example, is it cytokeratin positive? Is it EMA positive? Is it CD45 negative, as an example? But what we are anticipating is that as we go through this, we will come to a better understanding of truth as a result of the application of AI on these images. So things that we might not have thought were CTCs or circulating cells of the TME, we may come to a better understanding of that as we apply AI to these preparations.
Okay. Next one is from anonymous attendee. So in your non-small cell lung carcinoma study, how can we be assured that the attention maps in the non-neoplastic lung tissue are not false positive?
Yeah, that's a very interesting point. What we have been doing in our so-called sanity checks of this is actually asking the question, can we take areas of non-neoplastic tissue, have the AI just look at that, and will it be able to come up with a classification for metastasis or not? Our early data is that it cannot. And so we think that we believe that this is pretty specific to the tumor and the response to the tumor.
Okay. The next question is, for digital related research, you need IRB approval.
Yeah, we get IRB approval for all of the studies that we do in which we use patient specimens, even anonymized patient specimens. But as you can see from this research, in non-small cell lung carcinoma or CTCs, we are always linked to patient outcomes. So for those, for sure, we get IRB.
Okay. So the next one is, in light of telepathology, what's your thought on clear requirements on signing out at home in the future?
Well, I think that as long as the telepathology, what is happening is, first of all, there's FDA approval of certain systems, as you all know, and as systems get internal validation, I believe that there has not been and there will not be any particular problem with doing telepathology from any place in which you have an adequate screen in which to review.
Okay. Next one is, thanks for answering my question from Dr. Lee. And since you said scanners using FPM are here, what is the average scanning time for an FNA smear? It's like at 40x.
Yeah, we have not optimized. It's a very important question. We haven't really optimized this yet. And as you saw, the system that we put together is kind of a little bit of a Rube Goldberg kind of construction. What we are hoping for is that the scans will take place in a matter of minutes. Right now, it's quite a bit longer than that. And as you get to higher power, it can be very, very long. One of the things that we have noticed in digital image acquisition is that you may not have to go to the highest powers to get the kind of detail that you need even at 40x power. So that, you know, there may be some other advantages like that for the FPM.
All right. Next question is, can you share your thoughts on impact on the temporary CPT codes of the digital pathology on pathology practice?
I'm not sure I'm going to answer this question in the way that it was asked, but there are CPT codes for using digital pathology. The ones that are most commonly used are, of course, for quantitative assessment of, for example, HER2 or ER and PR. I'm not sure that I'm all that familiar with the temporary CPT codes. And so if somebody else is, I'd be happy to hear from them.
Yeah, I think that's all in the chat box. Yeah. I actually have a question. Okay.
Okay, go ahead.
Yeah. So, I mean, for sure, we realize like digital pathology is on the way, right? So what do you think about the impact on the future pathologist job market?
Well, yeah, that's a great question. And what I would say is that in my view, digital pathology is going to be a tool used by the pathologist as opposed to a replacement for pathologists. Now, there are attempts to, for example, do diagnostics. Some of you may be familiar with prostate cancer diagnostic programs that are being used. And so, you know, there will be incursions in that, but I suspect that those will mainly be used in underserved areas, in areas that don't have access to pathology expertise, where you would have both the impact of a AI algorithm and a pathologist's expertise to go along with that.
Okay. Thank you.
Okay, so Rich, actually, I do have one question. So I know time running out. Yeah. So, you know, for the digital pathology per se, I think, you know, we can adapt as long as we embrace the technology, you know, transfer our knowledge, you know, from a skill, from a physical microscope to a slide, you know, is an easy thing. For many audience, many people in the audience actually are academic anatomic pathologists.
Mhm.
So in the past, I know you have done a lot of work, like for example, for IHCs, right? So that is in our skill, because in our skill set. So now with this, our academic productivity, I would say, is going to be affected if we use those AI algorithm, because we truly, for small centers or academic centers, I wouldn't expect, there is a huge teams with those skills to deal with those computational sciences or the mega data set. So what's your view on those? I think the digital pathology democratizing the practice, but in some way is, is no, it's how to say, it's make, the academic productivity less for the general or average anatomic pathologist. So what's your thought on that?
Yeah, if I understand, Shuli, your question properly, and I'll answer it this way, and then if I'm not getting it right, please, we can explore it further. But I actually think it's quite the opposite. I think that so there's a couple of things to make the distinction of. One is research in this area, is the actual new knowledge acquisition, which would be the realm of the academic pathologist, right, and the academic medical center. And one is the application of these technologies. So in terms of the application, we now know we don't have to do research now to develop the ability, just the simple ability to acquire a high quality image at a speed that makes it diagnostically useful, right? That's been done, and it's being refined by companies. So we can apply those technologies to, for example, democratize access to pathology subspecialty expertise. But it's a very different thing to then say, okay, now I want to ask the question, can I use AI to help me in a risk classification for example, in your world, adenomas, for example, okay? Now that's going to be research, and I think that is going to be a very rich field of research where the academic pathologist can identify problems that they see in their practices that can now be potentially addressed using AI. Now, the access to that it's true. Not every academic center will have access to the algorithms and to the computational power that allows this, but that's always the case, right? The access to these technologies is not uniform, it's not universal, but in those centers that do have that access to, for example, that kind of computational technology, or on another example, to these highly multiplex molecular spatial profiling platforms, that becomes, in my view, a very rich source of new knowledge acquisition and academic productivity.
Thank you. Yeah, that answered my question, actually. Thank you very much. So because of the time, and I think we will end our program now. And thank you very much, Richard. It's an amazing talk. We truly enjoy. So we have an audience of over 170. So thank you. Thank you. Okay.
My pleasure. My pleasure. Thank you. Good night, everyone.
Okay. Bye-bye.